Hello everyone, we're about to begin our midterm exam review in this video. As a note, this video is going to be made up of different review videos that I have made in the past, but I have picked out the problems that are going to be more important for you on your exam, so it has been retailored to go ahead and have the relevant questions on your exam, if that is a hint at all. So these questions are going to be relevant to you in the very near future. So watching this video is going to be a great way to study, so hopefully you're watching the video. If you're already watching, then that's great. Other ways to study are going to be watching the other videos, going over the problems that we went over in those videos, also completing or at least working on the review assignment that is listed on Canvas. So for the midterm exam, we have a review assignment that is worth extra credit. It is under the extra credit module in assignments in Canvas. Completing any part of it would be worth extra credit. Completing all of it would be the most, but any part of it that you complete will be worth extra credit. Also, if you have anything that feels spotty, anything doesn't feel great before the exam, definitely feel free to email me and we can, discuss some things if you'd like. But so those are some key ways that we can hopefully study for the exam. But like I said, this video will have clips from other videos I've made in the past, going over problems that are going to be important for your exam. So these problems are going to be good to go over, beforehand. That being said, there are some questions in this. Ignore the actual numbering in these videos. Each problem will indicate what section it's from. It will have a label saying like section something, like section 6.3 and things like that. So every problem that you see, you'll know what section it's from, but the numbering on it will probably be a little messed up. So there we go. Without further ado, let's go ahead and review for our midterm exam. So in addition to the problems that we will be going over, it's also helpful to review these items on your own. So here a list of just the important topics from each section. So starting with section 1, we see vocabulary and specific equations, drawing angles in standard position, converting radians to degrees and vice versa. So radians to degrees and degrees to radians, finding the area, radius, or central angles to a specific problem. Then section 6.2, we see some vocabulary once again, and finding angles that correspond to points on the unit circle. Then section 6.3, determine quadrant of angles given the signs of the trig functions. So this is going to be, it will give you some sort of inequality for specific trig functions, and you have to determine what quadrant those angles are going to be in, or those hypothetical angles are going to be in. Then you want to find exact values of trig functions using periodic, even, odd, and or fundamental identities. Section 6.4, vocabulary again. Then we graph sinusoidal functions, find sine and cosine equations from given amplitude and period, and find equations for sinusoidal graphs. So given the graph, find the equation. Then section 6.5, graph functions of the form y is equal to a cosecant of omega x plus b, or y is equal to a secant of omega x plus b. Then use graphs of trig functions to determine characteristics of a function. So these are all the things that are going to be really helpful to go over on your own. Just review them from our lecture notes and lecture videos. Please go over like the different problems and examples that we did in each one of our lecture videos. And then this review, and you should be set for the first exam. Now for section 6.2, for problem number 2, we want to find 2 negative and 2 positive angles in radians that correspond to the point the square root of 3 over 2, negative 1/2. So if we need to find 2 negative, 2 positive angles that correspond to this point, we see that, or we can recognize that this point is found on the unit circle. And so what we can do from here is find that initial point, so the point that is actually on the unit circle in radians, or the angle from our unit circle in radians that would give us this point. We can identify that value first by either just looking at a unit circle, or we can do a few other things. If we don't have access to a unit circle at all, we can recognize what quadrant it's going to be in based on which numbers are negative and positive. Recognize what integer multiple it is of whatever specific angle measurement, and then figure out which value it's going to be considering the y value. So let's write those down first. So our first step in doing this problem is just to identify the base value, or kind of the base angle that we're looking at. So step one, we want to find the exact angle on the unit circle that corresponds to the square root of 3 over 2, or -1/2. So this is our first step, and we can do this by finding the value on the unit circle. Or if we don't have a unit circle accessible to us, then we can go ahead and do some deduction. So if we look at our point, we see our first value is positive and our second value is negative. This means that x is positive while y is negative. So we're going to say deduction. So from our points, we see x is positive and y is negative. This is telling us that cosine is positive and sine is going to end up being negative. But what we really want to know is what quadrant this point is actually going to be in. So if we see that x is positive and y is negative, this means that our point is in quadrant 4. And we know it's in quadrant 4 because if we drew out, and this is a little makeshift version of our unit circle, if we draw out our xy plane here, we see that, we see that quadrant 1, quadrant 2, quadrant 3, quadrant 4. We see that in quadrant 1, both values will be positive. In quadrant 2, we'll have negative x values, positive y values. Quadrant 3 will have negative x values, negative y values. And quadrant 4 will have positive x values and negative y values. So because of this, our point has a negative y value, positive x value. This means it's in quadrant 4. So we've determined that our point is going to be in quadrant 4. So the next thing we want to do is recognize what integer multiple this point is going to be at. And one hint that we can have is that integer multiples of pi over 6 have positive or negative y values of 1/2. So this means that we can determine that our angle has to be an integer multiple of pi over 6 in order to have a y value of negative 1/2. So let's write that down. So our point is in quadrant 4. Since our point has the y value negative 1/2, this means our exact angle is an integer multiple of pi over 6. And we'll say, because, and we're going to write IM instead of integer multiples, it's just a little bit longer, right? Because of integer multiples of pi over 6 have y values of positive or negative 1/2. Integer multiples of pi over 3 are going to have x values of positive or negative 1/2. So we see that difference there. With pi over 4, we see that both values are going to end up being square root of 2 over 2, either positive or negative. But that's how we can determine that our value is going to be an integer multiple of pi over 6. And if we know it's an integer multiple of pi over 6 and it's in quadrant 4, the only angle measurement that is an integer multiple of pi over 6 that's found in quadrant 4 is going to end up being 11 pi over 6. So we found the exact angle on the unit circle that corresponds to the point square root 3 over 2 over negative 1/2. If we had access to an image of the unit circle, this would be able to be found very quickly because all we would need to do is look for this point and then the angle that corresponds to it, it would have been labeled. But if we didn't have access to a unit circle of any kind, this is kind of how we would use deduction to go ahead and find that angle. So our angle is going to be 11 pi over 6. And now on to step 2, which we do not have much room for here. So let's go ahead and kind of scoot some of our problems down a little bit to create some more room. So we'll scoot this next problem down to about there. All right, so step 2. Let's see, where do we write this? Ooh. For step 2, now we actually want to, or we have to find more of these angles that would correspond to this point. So we already have one angle. We already have one positive angle, so this means that we need to find one more positive angle and 2 more negative angles that correspond, correspond to the square root 3 over 2, negative 1/2. And the way that we do this is we just have to find the next revolution, or the revolution before. So since we found that the exact value or the exact angle corresponding to this point on the unit circle was going to be 11 pi over 6, this means that the only other angles that can also correspond to this point would have to be the revolutions or negative revolutions around, because we know that 11 pi over 6, according to the unit circle, is the only point that can correspond, or the only angle that can correspond to this point. So this means that if we need to get this point again, we have to make revolutions. So we're going to add or subtract revolutions, put S in parentheses. We'll add or subtract revolutions to 11 pi over 6 to get what we need. All right, so our revolutions in this case we know are 2 pi. Since our denominator for 11 pi over 6 is 6, this means that one revolution is going to be 12 pi over 6. So this means that we're adding 12 pi over 6 or subtracting 12 pi over 6 from 11 pi over 6 to get our new angle measurements. So we need one positive value. So we're going to go ahead and we're going to add 12 pi over 6 from our original angle. This is going to give us 23 pi over 6. And this is going to be one of our angles. So now we have two positive angles. Now we need two negative angles. So let's go ahead and subtract. So we'll subtract 11 pi over 6. We're going to subtract 12 pi over 6. This is going to end up giving us negative pi over 6. So there's one negative angle measurement, and then we need one more. So 11 pi over 6. Now we need to subtract two angle measurements to get another negative angle measurement. We need to subtract 2 revolutions. So we already subtracted 12 pi over 6 from 11 pi over 6 once. Now what we can do is we can either subtract 24 pi over 6, that would be then 2 revolutions, or we can subtract 12 pi over 6 from negative pi over 6, which was our answer from our last problem. So it'd be up to you, but you can decide either way. So we're going to write 11 pi over 6 minus 24 pi over 6. This is equal to negative pi over 6 minus 12 pi over 6. So you can write this either way that you'd like, but either way, we're going to see that this gives us negative 13 pi over 6. And these would be the 4 angles that we needed that correspond to our given point. We can kind of sum up our answers here, over here. 2 positive, and we're going to write theta. So 2 positive angles, 11 pi over 6, 23 pi over 6. 2 negative angles are going to be negative pi over 6 and negative 13 pi over 6. So there we have it. Another way you could see it be written is in a list format. So where you see a list begin with your 3 dots, and then we go from decreasing to increasing order. So from least to greatest. So then we would see a negative 13 pi over 6, negative pi over 6, 11 pi over 6, and 23 pi over 6. And then same thing, more dots there. So you can see your answers written in any way like this. So all right, that wraps up our problem 2. So on to problem 3. We want to use the even-odd properties of the trigonometric functions to find the exact value of the given expression. And we want to do this without using a calculator. Let's move him up a little bit. We want to do this without using a calculator, so we're going to need to use our even-odd properties. So when we use our even-odd properties of cosecant, we know that cosecant also refers to sine. So cosecant of negative 120 degrees is the same thing as saying 1 over sine of negative 120 degrees. Sine, in this case, is an odd function. This means that if sine takes on a negative value, sine will then become negative. So now we can get negative 1 over sine of 120 degrees. So now we want to find the value of this problem. So this just means that we need to find the point that corresponds to sine of 120 degrees. If we want to do this, we could use the unit circle, anything along those lines. So sine of 120 degrees is going to be the square root of 3 over 2. This would be in radians 5 pi over 6. So now we have this value and we want to simplify as much as possible. So we have a negative 1 over the square root of 3 over 2. So we know that 1 over a fraction, we can just reverse the fraction. So this means that now we can have a negative 2 over the square root of 3. But we don't like having square roots in our denominator. So we'll multiply by the square root of 3 over the square root of 3 in order to get negative 2 square root of 3 over 3. So we use our odd property in this case, or the even odd property, but odd because sine ends up being odd. And so we were able to actually find the numeric value of this problem using the values given from our unit circle and knowing that when we take the sign of a negative value, we end up just getting negative sign of that value, the positive version of that value, which then we can easily find on our unit circle. So all right, that wraps up problem 3 from section 6.3. Now for section 6.4, number 4, we want to graph the function y is equal to 3 cosine of x. Show at least 2 cycles and then determine the domain in the range. So with 2 cycles, this means that we want to show 2 periods. And we're given this function y is equal to 3 cosine of x. So we're going to go ahead and use the method of using key points in order to graph this function. So remember with using key points, and we'll write this here using key points, we have 4 steps. 3 written steps, the 4th step is to graph. So when using key points, we want to start with step 1. And remember, step 1 is finding the amplitude and finding the period. So the amplitude is given to us by y equal to, in this case, cosine of omega x. And a, we see here, is equal to 3. So our amplitude, which we then take the absolute value of, is going to be 3. Then our period is given to us here. So our period is corresponding to the omega in the equation of form y is equal to a cosine of omega x. But since we see that we just have cosine of x, this means technically it's cosine 1 times x. So our omega in this case is just going to be 1. So we get that omega is equal to 1. Or here, we'll write this before. Omega is equal to 1. So when we find the period, we know it's 2 pi divided by omega, which is just 1. So our period of our function is still 2 pi. So just like in cosine normally, it has the period of 2 pi. This function also has a period of 2 pi. So we need to show for 2 cycles now. For step 2, we just want to take a period. So any given period that we want, we can take a period and then go ahead and sorry, mind blanked for a minute. We want to take this period and separate it into 4 equal subintervals. So we're going to take that period, divide it by 4, and that's going to be the length of each subinterval. So as an example, let's pick the total interval of 0 to 2 pi. So we want to divide into 4 equal subintervals. We know that our period is 2 pi, so 2 pi divided by 4 is going to be pi halves. So our subintervals need to be, or each need to have a length of pi halves, and we're looking between 0 and 2 pi. This means that our intervals are going to be 0, pi over 2, pi over 2 to pi, pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi. So these are our 4 subintervals that we're going to need to be looking at. Now, from our 4 subintervals, we want to go to step 3. Let's actually move this a little bit so we have some more room for step 3. So, step 3, we want to identify our key x values. Our x values in this case are going to come from our endpoints of our subintervals. So our endpoints are going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. So we're taking these x values, plugging them into our original equation to find the corresponding y values. So with our y values, we know our equation is y is equal to 3 cosine of x. So our first value will be 0. So we have y is equal to 3 times cosine of 0. So cosine of 0 we know is just 1, so this is just 3 times 1, which is 3. This means that our key point is going to be at 0, 3. Then our next value, pi over 2, we have 3 times cosine of pi over 2. Cosine of pi over 2 is just going to be 0, so we have 3 times 0, which is 0, which means that our next key point is going to be pi over 2, comma 0. Then our next value is going to be pi. Cosine of pi is going to be -1, so we have 3 times -1, gives us -3, which means our next key point is pi, -3. Then our next point is pi over 2. Cosine of pi, 3 pi over 2. Ooh, forgot that 3 there. So cosine of 3 pi over 2 is also going to be 0. So we have 3 times 0, which is 0, which means our next key point is 3 pi over 2, comma 0. Then our last key point here, we have y is equal to 3 times cosine of 2 pi. Cosine of 2 pi is going to be 1. So we have 3 times 1 is equal to 3, which means that our next key point is 2 pi, comma 3. So these 5 points here, these are our key points. So we need to go ahead and graph our key points. And remember, these are just key points for one single period. So once we graph these key points, we want to continue on our graph. And using our key points, we can fairly easily figure out where the points in our next period is going to go. So all right, let's start graphing. So we have points 0, 3. So if we go ahead, label our graph a little bit, 1, 2, 3, -1, -2, -3. We also have our -2 pi, -pi, pi, and 2 pi labeled, but let's go ahead and label pi halves and 3 pi halves as well. So all right. So our first point is at 0, 3. And our next point will be at pi halves 0. And our next point will be pi -3. Our next value is 3 pi over 2, 0. And our last point, 2 pi 3. And I want to go ahead and connect these points. So our graph is going to look something like this. And there we go. And that's for one period. Now, if we want to do this for 2 periods, we're going to take what we know from our first period here, and we're going to continue this on in the negative direction. So we know that cosine is an even function. This means that whether or not we plug in the negative or positive version of an angle, it's still going to give us the same answer. So this means that we have symmetry about the y-axis. So at negative pi over 2, our point will be at 0. Then at negative pi, we'll have negative pi, negative 3. Then at negative 3 pi over 2, we're going to have 0. And at negative 2 pi, we're going to have a positive 3. So now we can draw in these points as well. Ooh. All right, not as pretty as the other side, but we get the point. So our points here became 2 pi, positive 3, negative 3 pi over 2 comma 0, negative pi, negative 3, pi over 2, 0. This is 0, 3. And just like our original key points here, we had the same y values for the negative versions of our x values. But here we are, we have graphed the function of 3 cosine x. Now the last thing we want to do is determine the domain and the range. So with our domain, we're determining where our x values can exist. And actually, our x values will continue on forever. So our domain would be all real numbers, or another way we could write this would be from negative infinity to infinity. Then our range, we see our graph is going to alternate between all numbers between negative 3 and positive 3. So our range will be in our square brackets here, negative 3 to positive 3. And there would be our domain and our range of our function. So all right, that wraps up our problem 4 there from section 6.4. So now for our last problem, section 6.5, number 5, we want to graph the function y is equal to 4 secant of x. Show at least 2 cycles and then determine the domain and the range. So just like in our last problem, we want to show 2 periods of this, with now our function is 4 secant of x. So we're going to do the same thing as before. We're going to use our key points to go ahead and be able to graph this function. So using key points, step 1, we want to determine the amplitude and the period. So just like in our last problem, we can find the amplitude because it's this number that's being multiplied by our function. So our amplitude is the absolute value of 4. So our amplitude is 4. Then our period is 2 pi divided by omega, where in this case our omega is again just equal to 1. So we get 2 pi divided by 1, which is just 2 pi. So the period of this function is 2 pi as well. So on to step 2. Step 2 here, we want to divide our period into 4 equal subintervals. So we take our period, divide by 4 to get pi over 2. So each one of our subintervals has to have a length of pi over 2. So let's go ahead and look at between 0 and 2 pi. So this means that our intervals are going to end up being 0, pi over 2, pi over 2, 2 pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi. So here are 4 equal subintervals between the period 0 to 2 pi. And just like before with step 3, identifying our x values, our endpoints of our subintervals, they're going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. So the exact same x values that we had before. And now we want to find those y values. Our function is y is equal to 4 secant of x, so our first x value is going to be 0. So we have 4 secant of 0. So if we have 4 secant of 0, secant of 0 is going to end up equaling 1. So this means we're going to have 4 times 1, which is just 4. So our point will be 0 to 4. Then we have 4 secant of pi over 2. And if we notice, secant of pi over 2 is going to be undefined. So we can't use that value. So what we're actually going to do is identify which values here have to be undefined. So because cosine passes to the x value or has values of 0 at pi over 2 and 3 pi over 2, this means that we can't use pi over 2 or 3 pi over 2 as our x values. So this means that our next point has to be pi. So 4 secant of pi is going to end up being -1. 4 times -1, this gives us -4, which means that our next point is going to be pi -4. Then our last value is going to be 2 pi. So we have y is equal to 4 secant of 2 pi. Secant of 2 pi is just equal to 1, so we get 4 times 1, which is equal to 4. So we get our point 2 pi 4. So all right, we have our key points. We also know that our function is going to be undefined on pi over 2 and 3 pi over 2. So we can draw in our vertical asymptotes. So according to our graph here, let's go ahead and mark this up a little bit. This is going to be pi over 2. This is going to be 3 pi over 2. So then this will be negative pi over 2 and negative 3 pi over 2. Then we have 1, 2, 3, 4, 5, 6. And -1, -2, -3, -4, -5, and -6. So we draw in our vertical asymptotes of pi over 2 and 3 pi over 2. So first things first, we're only considering our period from 0 to 2 pi first, and then we'll consider another period. So our first value, we have 0 to 4. Sorry, our first point is 0, 4. And we know that the key attributes of graphs of cosecant and secant are going to be that they look like parabolas between given vertical asymptotes. Since our graph of sine or cosine has those curves, we see that they connect at the tops of those curves and they become parabolas. So since we're given a non-negative version of secant, we can say that at this first point, 0, 0, 4, this is going to be an upward facing parabola.
But if this is going to be an upward facing parabola, we should draw in our next vertical asymptote. And our next vertical asymptote would then be at negative pi over 2. Since secant is just 1 over cosine, this is also an even function. So our values are going to be the same. So we have a vertical asymptote at negative pi over 2, and then we're going to have also another negative asymptote, a vertical asymptote at negative 3 pi over 2. So this first point, 0, 4, is just telling us where the base or the minimum of our upward facing parabola is going to be. Let's try that a little better. There we go. So there's our first value. Then our next key point is going to be pi negative 4. So negative 4 is going to be then the maximum value on our downward facing parabola. Then our next value is 2 pi positive 4. Our plane kind of ends here, but we can go ahead and draw this side of our parabola. We can draw the next side of our parabola if we would like as well. All right, so this covered a little bit more than one period considering that we went back to negative pi over 2. But now we can continue on using the formulation that we've already kind of created. So we know that our function secant is an even function. This means that if we plug in negative pi into 4 secant of x, this would also give us the value of negative 4. Then if we did the same thing with negative 2 pi, it would then give us a positive 4, so we can go ahead and draw these in too. So this would be negative 2 pi positive 4. This would be negative pi negative 4. This here we know is 0 positive 4. This is pi negative 4. And then lastly we have 2 pi positive 4. So this here is definitely covering 2 periods, or 2 cycles of our function. So step 4 we've now completed. We have graphed our function. Then the last thing we wanted to do was determine the domain and the range. So our domain and our range in problems such as these are going to be very specific, and they need to be written in our set builder notation. So our domain we write as x, where x has the property, and we're going to say x can't be equal to the values that we see on our vertical asymptotes. So in our vertical asymptotes, these are 3 pi over 2, pi over 2, negative pi over 2, and negative 3 pi over 2. So we see that these are going to be integer multiples of pi over 2, but more specifically, they're odd integer multiples of pi over 2. We're seeing 1, 3, if we continue, we see 5, 7, 9, 11, and so on. So x cannot be equal to k pi over 2, where k is an odd integer. So that would be our set builder notation stating our domain. We know that x can exist everywhere except for k pi over 2, where k is that odd integer. Now looking at our range also needs to be put into set builder notation. So we have y, where y has the property of, I'm not going to write equal sign. We see that our parabolas, our upward facing parabolas, could be 4 or more, and our downward facing parabolas are going to be negative 4 or less. So when we write this, we're going to write y less than or equal to negative 4, or y greater than or equal to positive 4. So this means that our values of x and y can exist all of these places written out in our property for our set builder notation. And those would be our answers there for our domain and our range. So in addition to the problems gone over in our review, it's also going to be helpful to review some of these items below on your own, as well as the problems that we're going to go over today. All right, so for section 1, we want to focus on finding the exact values of an inverse trig function, finding the exact values of composite trig functions, and then solving equations involving inverse trig functions. So we're really just working with these different inverse trig functions and then solving equations that are actually going to contain them. Then section 2, we want to find the exact values of inverse trig functions again. So just to make a note of this, in section 7.1, when we talk about finding exact values of inverse trig functions, that's going to be sine, cosine, tangent. For section 7.2, with defining exact values of inverse trig functions, that's going to be with secant, cosecant, and cotangent. Then we want to focus on writing trigonometric expressions as algebraic expressions. So remember, that's taking our trig functions, rewriting them into their algebraic forms, and then being able to finally write it in some sort of algebraic way, most often going to be of one variable, maybe some other numbers as well. Then finding exact values of mixed composite trig functions as well. So that's still going to be with your composite trig functions. They are just varied. So you can have a mixture of them. Section 7.3, we want to find approximate solutions to trig functions. So that would be using a calculator. Whenever you're asked to find approximate, that's going to be calculator. Solving trig equations with more than one trig expression, so multiple trig expressions then. Finding solutions to trig equations in the interval 0 to 2 pi. So then that would be finding the solutions in just the interval 0 to 2 pi, so that's when you're going to be dealing with your solution sets. Section 7.4, we're establishing our trig identities. So this is when we have a statement or an equation set up and you want to follow along to try and end up with the goal part of your equation starting from a specific point. So establishing a useful identity that you can use in the future. Section 7.5, we want to use sum and difference formulas to solve for exact trig expressions. So everything is basically a review now. We're just also including the sum and difference formulas included within everything that we've gone over so far. And lastly, section 7.6, we want to be identifying properties of double and half angle formulas. So this is just recognizing what they look like and recognizing their formations when you write them out. So the exact formulas specifically. And then we want to use our double and half angle formulas to find exact values and also to establish identities. So using those half angle and double angle formulas help us establish certain identities, and also we can use them to find exact values. All right, for our fourth problem, which is from section 7.4, we want to establish the identity cosine of theta minus secant of theta is equal to negative sine of theta times tangent of theta. So when we go ahead and establish our identities, we know that one side is our goal and one side is where we start from. It's usually going to be our right-hand side. That's our goal. And our left-hand side is usually where we start. This isn't always the case. Sometimes they may be switched, but it's always easier and better to look for whichever side looks more complicated, then that's where you'll start. Because it's much easier to simplify than it is to expand. So in this case, they look about the same. So this just means that we could pick either one to start from and which one would be our goal. So we'll just stick with the right-hand side is the goal and our left-hand side is where we start. So we're starting with cosine of theta minus secant of theta. Our first thing that we want to do is we just want to start simplifying. We want to start simplifying and rewriting terms. So if we have cosine of theta minus secant of theta, there's no clear way that we can rewrite cosine of theta just yet, but we can rewrite secant of theta, which we know secant of theta is just 1 over cosine of theta. So now we have both terms in terms of cosine. So we can now combine our two terms into just one term. And in order to combine them, we would need to rewrite cosine of theta as cosine squared of theta over cosine of theta minus 1 over cosine of theta. And now we can rewrite this so we just have one term instead of two terms, and this gives us cosine squared of theta minus 1 divided by cosine of theta. So this is what we're left with. All we've done here is we simplified, we rewrote our terms, and then we combined them. Now what we want to do is we want to use an identity we already have. We want to use the identity cosine squared of theta plus sine squared of theta is equal to 1 to replace cosine squared of theta minus 1. So if we have cosine squared of theta minus 1, if we want to rewrite this problem, we can end up with a sine squared theta, but this is going to give us 1 minus cosine squared of theta, and we have cosine squared of theta minus 1. So if we just want to flip those terms, we can now say negative sine squared of theta. This would give us negative 1 plus cosine squared of theta, which we know we can just rewrite as cosine squared of theta minus 1. So we can replace cosine squared of theta minus 1 with a negative sine squared. So we replace cosine squared theta minus 1 with negative sine squared of theta to get negative sine squared of theta divided by cosine of theta. And remember, our goal is to get negative sine of theta times tangent of theta. We do have a negative sine theta, we just have a negative sine theta squared. So we have also a denominator of cosine of theta, and we know that tangent of theta is equal to sine of theta over cosine of theta. So let's go ahead and split up our sine squared. If we do that, we can pull the negative sine of theta out and leave the positive sine of theta over cosine of theta, which we then see is equal to tangent of theta. And this would give us negative sine of theta times tangent of theta. And that establishes our identity. So we started with cosine of theta minus secant of theta. All we did was wanted to simplify, rewrite our terms as much as possible, combine our terms, use our other identities that we know to, once again, just rewrite, keep rewriting those terms until finally we got to negative sine of theta times tangent of theta. So, all right. Problem number 5 from section 7.5, we want to use the sum or difference formula to find the exact value of cosine of 5 pi over 12. So we know from the get-go we're using the sum or difference formula to find this problem. And remember, our sum or difference formula for cosine would end up looking like cosine of alpha times cosine of beta, depending on what you were using, plus or minus sine of alpha times sine of beta. So there are plenty other ways that we can separate out 5 pi over 12. You can use the difference formula, you can use the sum formula, whichever one that jumps out to you first. You just want to make sure that the values that you're adding or subtracting are going to be values that you can easily find on the unit circle. So that's the main key that you really want to be doing in that case. So we can start off by getting that 5 pi over 12 is going to be the sum or difference. So the sum or diff of two angles, which remember we call alpha and beta. And these angles need to have values related angles are known. This is just to say if you're going to split up 5 pi over 12, if you're going to split up 5 pi over 12 into two different angles, these two angles should really be found on the unit circle so that you can know what they are and what their related angles are going to be. So you can split 5 pi over 12 up many ways. The one possibility, and the one that we're going to use, is going to be 5 pi over 12 is going to be equal to 2 pi over 12 plus 3 pi over 12. And 2 pi over 12 simplifies to pi over 6, and 3 pi over 12 simplifies to pi over 4. So two values that are found on the unit circle. And that's the key there. If you split up your current angle into two angles that maybe aren't on the unit circle, it's just going to be that much harder to actually solve the problem since you can't easily just refer to the unit circle to solve it. So that being said, we're going to use pi over 6 plus pi over 4. Then we get that cosine of 5 pi over 12 is going to be equal to cosine of pi over 6 plus pi over 4, which then using, in this case, our sum formula, this is going to simplify to cosine of pi over 6 times cosine of pi over 4 minus sine of pi over 6 times sine of pi over 4. So remember that our formula looks like cosine of alpha plus beta is equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. So remember that's what our formula is. So we're using our sum formula to rewrite this. Now all we need to do is solve for our new values. So really quickly, we can state what each one of these values are. We can state that cosine of pi over 6, this is going to end up being the square root 3 over 2. Cosine of pi over 4 is going to be equal to the square root of 2 over 2. Sine of pi over 6 is going to be equal to 1/2. And sine of pi over 4 is equal to the square root of 2 over 2. So this means that cosine of pi over 6 plus pi over 4, using our formula that we had before, is going to simplify down to square root 3 over 2 times square root 2 over 2 minus 1/2 times square root 2 over 2. Simplifying this down, square root 3 times square root of 2 is going to give us a square root of 6 over 2 times 2, which is 4. And 1 times the square root of 2 is going to be 2 divided by 2 times 2, which is 4. And lastly, we can combine these terms to end up getting the square root of 6 minus the square root of 2, all divided by 4. So that would be our answer there, but just writing this as our final answer, we get cosine of pi over 12 is going to be equal to the square root of 6 minus the square root of 2 all over 4. Another way you could rewrite it is that you could rewrite 1/4 times the square root of 6 minus the square root of 2. Either way, they're the same thing, but whichever way you prefer to write it out. So, all right. So when using sum and difference formula, it's really just being able to correctly pick out what two angles you need to be able to use, and then just using the formula.